we're doing right. There we go. Alrighty. This whole unit is looking at what goes inside of an atom. Alright, so we call this subatomic particles. That's because, think of sub like submarine. Submarines go beneath the water. Subatomic particles is what is happening inside of an atom. Okay. Problem is that when you deal with subatomic particles, either A, they're extremely radioactive, which means you're likely to develop cancer around them, or die, or B, they're highly explosive. So here's what I'm going to say is, we're probably not going to have very many labs during the next few weeks, just because I don't have any radioactive stuff for you to die with. And I prefer not to the lab explode just at all. So we might incorporate just some labs that way. I'm not beating you to death with simulations and bookwork-ish kind of stuff. All right. But there will be 2 homeworks which are available right now. The atomic modeling activity is available right now. And then Thursday, I'll have a history of the atom reading for you. At some point, we have to talk about where we discovered the atom and all the steps to it, which is what that reading is going to be over. But I will not put it on a quiz or a test, just because it's history. Do we really need to know about what we had wrong a couple hundred years ago?
No.
Not really. But do I have to talk about it? Yes.
Why do you have to talk? Can't you just say you talked about it? Like, I don't understand why teachers are always like, we have to do it. Like, couldn't you just, like, talk about it for a second and then be like, okay.
You're going to do it for a day and then never going to talk about it again. That's it.
What's this?
Okay. Subatomic particles and ions. We're going to do a lot of different things here today. Okay. Remember, white background is notes, black background is not. All right. First started off is some really old philosophers. What we got? I think I put the date on here and I forgot to. Sometime BC. You had Aristotle and Democritus. All right. Both these guys were saying, okay, if I take a rock, I cut it in half. I take a rock and I cut it in half. Take a rock and I cut it in half again. We get to a point where I can't cut that rock in half anymore. We're at the smallest piece of matter. And so they coined this term as atomos, which is where the word atom comes from, meaning indivisible. However, shortly afterwards, a couple hundred years later, we disproved them. All right. Fast forward a couple of scientists. All right, and you're going to do those more in depth on Thursday. We got Dmitry Mendeleev. All right. Crazy Russian dude, had a terribly difficult life. His whole life was terrible. I mean, he just had one bad thing after another, after another, after another. And I think he had like this vengeful idea of like, I'm just going to disprove every scientist I ever find ever. So he eventually made it to a university, started doing publishing all these papers, and he was just really bent on organizing the periodic table. And by doing that, he said, you're wrong, you're wrong, you're wrong. I can't tell you why, but I'm just going to say you're wrong. And then, 150 years later, we're still sticking with what he says. Yeah?
Who was the guy with the pea pods?
The what?
Oh, yeah.
The guy who did the pea pods and he became a priest?
That is Gregory Mendel.
Okay.
The father of biology. Yeah.
What was so bad about his life?
He was an orphan. Then he lost his family in a fire. Became an orphan. Was on the road for a lot. His wife died of cancer right after he got married, I believe. Like the dude never had anything going right for him. I think there's something else that happened. But now let's talk about, fast forward all the way through all that stuff. Where are we at today? All right? And I recommend you draw this picture out. Okay? This picture explains a lot of information, and I'm going to be here for a pretty long time. All right? There are 3 subatomic particles. The reason I don't want you to Google anything in this class is because if you Google subatomic particles, you will find things that we will not talk about in this class. All right? Like gluons and quarks and quasons. We're going to say 3 subatomic particles, and we're going to call it done there. If you're interested and curious, go study nuclear chemistry. But I'm going to call it, we have 3, We're going to unpack those three, what they are, what they represent, and then we're just going to move forward. All right. So, in middle school, you should have talked about protons, neutrons, and electrons. Did you guys do that?
Yeah.
Do remember that. Fantastic. Protons are positive, neutrons are neutral, electrons are negative. Are we good there? Hey, look at that. Maybe I don't have too much teaching today. I will. It will get crazy. Okay. We are going to say that the mass of a proton and a neutron is 1 AMU. AMU stands for atomic mass unit. I'll show in the next slide what the true mass of a proton is and why we won't use it. It's an extremely small number. Because of an extremely small number, to prevent us from doing, I'd say, really chaotic math and being lost a lot, we're just going to say, we're going to call it 1. 1 AMU. And electrons are so much smaller than a proton that we just essentially call them 0. So for the sake of this class, we're going to call them 0. Now, the one thing I do want you to be cognizant of, and this is why we're drawing this picture, is where are the protons and the neutrons located? And that's in the nucleus of the atom. So when you study nuclear chemistry, you're studying what kind of chemistry happens in the nucleus of an atom. So atomic bombs, nuclear power plants, you're playing around with what's going on with these protons and neutrons. All right, not really the electrons. Electrons are just kind of in your way for nuclear chemistry. And then what are the electrons doing? The electrons are floating around the outside. They're bouncing around like a wild child. So I like to use this as a representation. Have you guys seen those parents with like kids on leashes?
Yes.
You got the big tall parent. The big tall parent is the nucleus of the atom. All right? What is that little kid doing? He's running all over the place, but is latched to that leash. That's what an electron does. It is super energetic. It is high energy. It is ready to roll, and it is bouncing all over the place in this cloud. It will never go farther than the cloud because it's attached by a leash, by a force that's holding it in. All right? But it'll go super fast. It almost travels the speed of light. Albert, you have a question?
Can I put kid on the leash under electron?
Sure. Get on a leash. All right? Protons and the neutrons, they hold hands together through a strong nuclear force. We don't really unpack that because that's more physics. But they hold together. There's a very strong force holding all of those together. All right? So here's essentially what we're going to do for this whole week. What happens if I change the number of protons? What happens if I change the number of neutrons? And what happens if I change the number of electrons? If you can answer that question very smoothly, you've nailed everything we're about to do. Okay? Did I buy enough time on the slide? Are we still writing down?
I'm so drawing.
Okay. I believe, don't quote me on this, this is the only picture I have you draw today. Okay. In middle school, did you guys talk about ions at all?
I recognize that name.
Like
that.
remember
Yeah.
the word. Isn't an ion when like it has one less electron and then something else has one more?
Yes, we're going to get there. There's
Wait,
cations and there's anions.
Yes.
Yes,
Okay.
absolutely, we're going to get there. Maybe what you did in like 3 weeks in middle school, we're all going to do today.
Oh no.
All right? This is real chemistry class. I got excited writing these notes. Like I haven't done real chemistry in a couple years because I've only taught physics. So this is fun.
Is chemistry your favorite?
No, physics is my favorite because you can do more labs. And we pull up the Nerf guns for physics class. Like, am I good to move on? I hear some chitter chatter, so I'm moving on. Okay. All right. Oh, I went too far. There we go. Here's the actual mass of a proton, neutron, electron. All right.
Do we have to write that down?
No. Okay. This is, if I put 23 zeros in front of that number, that's how many grams it is to produce one proton. So preventing us to do all this math, we're going to say, you know what? Not going to do it. All right?
Yes.
if you want to, you can simplify what you've just written down as what we call a proton has a positive charge and its mass is 1. That's it. Neutron has a charge of 0, mass is 1. Electron, tiny little kid on a leash, has a negative charge because the kid's in a bad mood all the time, right? And has a mass of 0. Cool? Alright. I recommend you pull out your periodic tables and you write this on your periodic table. Alright? This is one of those things we're going to add to our periodic tables today. Just this little square, somewhere off to the side, doesn't matter. Put number at the top. No, like off to the side, only on that white space on the page. So for example, up on this one, this person put on the bottom left side. Totally fine. All right. Now let's talk about what does our periodic table tell us about an atom. The very top number is called your atomic number. If it is an element, it has a very specific atomic number. That number cannot change. If you change that number, you change the element. The symbol, which we've kind of hit on already with balancing chemical reactions, you understand as the symbol tells you what element it is. But then,
write the protons, neutrons, and electrons thing on the side, like on our notes?
yeah. Okay. And then the atomic mass is that number at the bottom. So if I have one carbon atom, it is 12.011 AMU. Okay. So you can't look at an atom and count how many protons, neutrons, electrons there are in this class. What we will use is the periodic table to tell us what information is there. So how do you figure out the subatomic particles in a neutral atom? Super easy to do the first one. The number of protons is the number at the top. And we're going to do some examples as a class here in a second. You get chances for candy, that won't have to talk all day. So if you look at carbon, on every periodic table ever in existence, 6, right, is written at the top. That's because carbon always has 6 protons. How do you figure out the neutrons? Well, the protons and the neutrons are the only things that have mass. So if my mass in total is 12, rounded, and 6 of that is the protons, well, 12 minus 6 gets you your neutrons. All right, I'm going to slow down. I'm getting excited. I'm speeding up. Dawson, did you find that third stool back there?
Yeah, cool.
Got those on sale. $5 a piece.
From where?
Bargain bin. I got way too excited.
Where?
Bargain bin? It's in Muncie. I pointed at him. I said, "How much are those?" She says, $10 for the pair. I was like, sold. I didn't know we were negotiating, but apparently we were. You okay, Dawson? You look a little exhausted. Did you have a good weekend? Did you have too good of a weekend? Okay. All right. Your atomic mass, which is the total mass of that atom, is protons plus neutrons. So I'm going to write this also down here as protons plus neutrons equals atomic mass. These are your notes. I'm not checking them. And then also, if neutral, protons equal electrons. So for carbon, it's super easy. Carbon's nice and balanced. You have 6 protons, 6 neutrons, and 6 electrons. Yeah. AM for atomic mass. Okay. Somebody go ahead and ask the question. Why is it 12.011? Fantastic question. We'll talk about that here in a second, because carbons sometimes like to be fat some days, and some days it likes to be skinny. So you have carbons that have different amounts of weight to them. All right? Sometimes it's had a cheeseburger and it's radioactive. Sometimes it's a little thin and it needs to eat a cheeseburger and it's still radioactive. All right? We'll talk about this in a second. But for right now, here's what I want you to do. That number at the bottom, you just round it to a whole number. Okay? Ready for some practice examples?
I think so.
Yeah? This will make a whole lot of sense here in a second. Got oxygen. Oxygen on your periodic table is at 16. What number does it say?
Let's see.
Oxygen's on the right side.
15.99994.
15.99994, which rounds to 16. So now let's figure out what's the number of protons for oxygen?
8.
8. Dawson, how do you know that?
Top number.
What's the top number mean? The top number is your blank.
Atomic number.
Atomic number, absolutely. Is atomic number the same thing as atomic mass? No. Atomic number is the top, atomic mass is the bottom. All right, Dawson, this will be the farthest throw I've ever had in this classroom.
Oh gosh.
Ah, nick the ceiling. There's a reason I get dum-dums and anything else, because dum-dums tend to not break. All right. Protons, easy. So I got 8 positive pieces in an oxygen atom. All right. Number of neutrons. What's that going to be? 8. And how do we get there? I've lost my pins already. I heard a bunch of mumbles.
Atomic mass minus the atomic number.
Absolutely. Kingston said it perfect. Okay, atomic mass minus atomic number. So we got 8 protons, 8 neutrons, and we got 8 electrons. Okay? Because it's neutral right now. Ready, King? Shirt's a little tight today, so I'm going to blame it on the shirt. Okay. Yeah. Go ahead and ask the question.
How do you know if it's neutral?
Right now, we're just calling it neutral.
No matter what we do.
Right now, yeah. We're about to change it, but that's going to be towards the end of the notes.
Okay.
Okay?
What about when we like do our assignments and stuff like that? How will we
You will know. It'll say oxygen has a -2 charge. How many electrons does it have? Which we don't know how to do yet, but you'll know. Okay? Good here? So somebody go ahead and ask the question. Are these always the same number? Maddie! The computer lab? Which computer lab? The computer office? Okay, fantastic. Maddie, do you know where the old middle school office is at?
Yeah.
Will you take her there? Thank you. She's going to lead you there, because it's little left and right, some turns, and I'll make sure you get there, okay? It's Mr. Davis's new office, but it's down there.
Yeah. Wait. Middle school?
Where the middle school office used to be. Okay.
I just got so confused.
But
I just got so confused. I saw a child. It was between 6
they
and
think middle schoolers that small? I mean, I'm not tall to begin with. Anyways, okay, all right. Emmy, what about?
If they're neutral, it's the same number of protons and electrons, right?
Yes, but so I asked the question, and Maddie helped me out, but you can ask the same question too. Are these always going to be the same number? No. We're going to shoot an example here in a second. Okay? Let's change it up a little bit. Let's do aluminum. Kingston, follow with me.
Got you.
How do I find the number of protons? Emmy, you got that?
Oh god.
It's the easy one.
Wait, what is it?
Number of protons. You look at the atomic number, which is the number at the top, for aluminum.
And then you subtract it, right?
Nope, just the top number is your protons.
Oh, okay.
Did you find aluminum?
Yeah. So that's gonna take me a while.
It's
no,
okay.
I found it.
You found it, cool.
Yeah.
What's the atomic number for aluminum?
13.
13, absolutely. So the top number always tells you your number of protons. Fantastic. Now, at the bottom of on your periodic table, it should say 26.981538. What do we round that to, Emmy? 27. It's just making a nice, pretty whole number, okay? Ready? I'm moving on to somebody else. Okay, you can breathe easy. All right. The shirt. It's your fault too. I don't know why. But. Okay, let's do a number of neutrons. Abby. I'm gonna call him Dawson because he has his hand up. He wants some candy today. He wants some candy. Just want to answer the question.
I want some.
Okay. Help me out. How to find number of neutrons?
Subtract the atomic number.
Absolutely. 27 minus 13, atomic mass minus atomic number equals 14 neutrons. Fantastic.
Can I do the electrons?
You want to do the electrons?
Yeah.
You want to do the easy ones, don't you?
It's just 13, right? Because it's the same as the.
Absolutely. If it's neutral, protons and electrons are the same number.
Can I have a Smarties?
Sure. Okay. There we go. Yes, Kenzie.
Good word. How do you know if it's neutral or not?
Right now we're calling all of these neutral.
So is it neutral?
Yes. I haven't said like aluminum with a +3 charge.
Oh, that's what.
We
it's
haven't
not
said
neutral?
anything about ions yet. We haven't said anything about charges. But right now we're calling all of them neutral. Good questions though. We good here? Alright.
Not this one. Some sort of.
Alright, moving on. Thank you, Maddie.
I'm scared.
Did great.
She's.
We did one example while you were gone, but I'm pretty sure you're good. Okay. Alright. Now let's answer that question. Why are there decimal values for atomic mass? Remember I told you carbon can sometimes be fat one day and sometimes really fat the next day, but some days it's normal. Okay. We're getting into a brand new word, isotopes.
Do you want to write this all down?
What's that?
Are we writing this? Yeah.
These are your notes. Okay,
I
these
know,
are
I
also
just
available
didn't know
on
if it's
Schoology
great.
as well, okay? These are your notes. Okay. Isotopes have the same number of protons. Carbon is always carbon. Right? So if you change protons, you change the element. So carbon will always have 6 protons. Right? But it has a different number of neutrons. If you have too many or not enough, they can become unstable. So you get unstable isotopes, which is where stuff gets radioactive. When the Fukushima nuclear reactor had a tsunami hit it, all of that radioactive, uranium, and I think it was uranium, on the inside, made the water unstable. And how did it make that water unstable? Is it took some of the hydrogen and oxygen in there and added more neutrons. When that happens, some crazy energy's flying off and your DNA gets ripped apart and rewritten, which is why you get cancer around radioactive materials. Okay. So the decimal value is calculated by the ratio of how often those elements are naturally found. So you may have heard the term carbon dating. It's not where you date carbon. Hannah, do you know where you've heard the term carbon dating?
Isn't it with like trees and stuff?
Absolutely, and dinosaurs. Okay. So what do they do with carbon dating? They look at how many of these unstable atoms are in there. With some math and some other stuff we'll do like in a few weeks, right? We're able to predict how old something is based off of the carbon that's inside of it. So you can do carbon dating on anything that's living. It could be an animal, it could be a plant. You can do carbon dating to see how old it is. Which is where if we dig up a dinosaur and we do some carbon dating on it, we can say this dinosaur is approximately however many million years old. Good here, Dawson? Cool. So here's what I want you to think of. When you hear isotopes, think of atoms getting too heavy, too fat, or too skinny. The number of protons and what they are on the inside stays the same. But have they eat a cheeseburger or they lost some weight, they get unstable. All right? Like if I eat too many cheeseburgers, I get unstable, have a heart attack, and then something bad happens. Yeah, Hannah.
So the only thing that can change are the neutrons, right?
Absolutely.
Why can't the protons or electrons change?
If you change the protons, you change your atomic number. So look at, on your periodic table, look at nitrogen. So if I take carbon and I add a proton, it turns into a new element.
Oh, okay.
Follow me there?
Yeah.
Absolutely. It's a good question. So if you change the number of protons, you change the element. If you change the number of neutrons, you change the mass and how fat or skinny it is, but it's still that element. We good here? Things are looking great. I'm looking good on time. Nope. All right, don't draw this picture, but I want to talk about water. Don't draw this picture, you don't have to. All right. When you look at that heavy water on that Fukushima disaster, those hydrogen atoms became what's called heavy water. Why is it called heavy water? Well, here's what normal hydrogen is. It's got one proton, one electron, it's happy. However, when you give it some more neutrons, it gets a little heavy, it turns into a different type of hydrogen. All right, this won't show up on a quiz or test. But I'll explain this. What exactly is heavy water? Well, if it's really radioactive, we throw a lot of neutrons at it, right? It becomes a heavy hydrogen atom. Since it's a heavy hydrogen atom, and there's hydrogen in water, it becomes heavy water. Heavy water is extremely radioactive, and so that's why I thought this was really interesting. The elderly, to help clean up from the area, they decided to go clean because if they ingested or took in some of this radioactive material, they're already probably going to die soon anyways. So they wouldn't have the effects as if a 20-year-old walked in there and did the same thing, they would probably develop cancer in 15 to 20 years. So I thought it was super cool, is that all of the elderly population took care of the younger population and they cleaned up after it. And that's because all of the heavy water in the ocean, right, they helped pick up all those pieces. I thought it was super cool, but I'm moving on. All right, here's what I expect you to do with it. Here's some practice problems, okay? It's kind of what your homework's going to look like. I'm going to say isotopes, and we have carbon-12. Notice how this is written. It's carbon-12. So we got carbon-12. So you look at your periodic table. Do you have a periodic table, Savannah? Okay, probably going to need it here in a second. Mary Kate, ready? I was going to call Savannah, but she's not ready. She doesn't have a periodic table up. All right, look at carbon. What's the atomic number of carbon? 6, absolutely. Regardless of what type of carbon it is, it's going to have 6 protons. This is neutral, so how many electrons are there going to be? 6. Whew, man, tough stuff. All right. Now, carbon-12 and carbon-16, I tell you what the mass is for carbon-12. Ready? The mass is 12. So to find the number of neutrons, we're going to take carbon-12 minus 6. 12 minus 6 gives you 6. Good there? I did it once, now you do it. You got carbon-16. How many neutrons are going to be in carbon-16? Absolutely. You just take 16 minus 6, get you 10. 10 neutrons. That's it. Good there? Cool. Yes, Maddie?
I'm so confused. How can the mass be different? Like, for carbon, how is it sometimes 12?
How does it become fat? I'm going to use that word. How does the mass become different? Is through a radioactive or nuclear chemistry reaction. We're going to cover those, not today. Okay? In the same way I just told you, hey, this is just a balanced chemical reaction, just believe me. The same thing here is, we'll get there, just not today. All right? All I'm going to say is an isotope is an element with different number of neutrons. How are they there? We'll get there in like 3 weeks. Okay. I think it's really cool stuff. It's literally nuclear chemistry, but just take one step at a time. Some people are already like, their brains a little melted already. All right. I'm going to pick on Savannah. I'll pick on Savannah. I'll go back to Savannah. All right, Savannah, we've got nitrogen 15. Find nitrogen on the periodic table. How How many protons are in nitrogen?
7.
Fantastic, and it's always going to be 7. It's neutral, so how many electrons are there?
7.
Woohoo! Hot dog. Now I've got nitrogen 15 and nitrogen 20. Which one? What's my number of neutrons for those?
Nitrogen 20 would be 13.
Absolutely.
And then oxygen 15 would be 8.
8. Fantastic. There we go. All right. All you do is take your total mass minus, all right, your number of protons, and that tells you number of neutrons. We good here?
I think so.
All right. That's what one of your homeworks look like. I'm going to put a pause on this. I'm going to do it first thing tomorrow because we're running a little behind schedule now. All right. Don't write this down. It's not going to be a quiz or test, but I do want to talk about where does this stuff pop up at because you guys love to ask good questions. All right. What makes an unstable atom useful? Really has two, in the top of my head I can think of is two big uses in medicine. I'm assuming there's more. If you ever go into an MRI machine and make you take a pill or a syringe of iodine 137, which is heavy iodine. In the MRI machine, that's what the MRI machine reads, is where is that iodine 137 at when you're in that machine. Or radiation therapy for like chemotherapy is, it is targeted cell death with radioactive elements. I don't know which element off the top of my head, but, and then some other uses for nuclear chemistry, nuclear bombs, or
Warfare.
or nuclear power plants. Which the closest nuclear power plant to us is not that far away. It's at Purdue. So if you want to study nuclear chemistry and nuclear engineering at Purdue, you can literally get to play with a nuclear power plant. All right. We good?
No.
A little bit. This is more of summarizing what we've done so far. Okay. Protons. If you change the protons, you change the element. Okay. Neutrons. If you change the number of neutrons, it becomes, all right, heavier or skinner. The mass already changes. All right. You have this written down. If not, I'm moving on. What happens, and this is new stuff, if you change the electrons? Okay. So this, I would recommend writing this one down. Okay.
We do have to write this.
Okay. We're going to skip this part though for now. No, it's the computer's going too slow. I'm asking way too much of the computer right now. I plugged a 12-year-old computer into a brand new board. Okay. What happens to electrons if the same number of protons, neutral? So you think of protons as a good mood, electrons as a bad mood. If I have the same number of bad mood to good mood, I'm just vibing. I think that's the word I would use there. Just chilling. But if we think of electrons as a bad mood, if I were to gain a bad mood, I become negative. If I were to lose electrons or lose a bad mood, I become positive. Think of the electron as a negative 1. So if you change the protons, you change the element. Change the neutrons, you change the mass, which is an isotope. If you change the electrons, you change the charge. And the charge becomes an ion, which is what's on the next slide. Okay. Most of the chemistry we'll do after this unit will be with dealing with electrons. That's because electrons are the easiest to remove. It's a whole lot easier to remove that thing on the very outside edge as it is comparing trying to move something in the middle. Yeah, what's up, Hannah?
So no matter what, if it gains an electron or loses them, it's still called an ion?
Still called an ion.
Okay.
What kind of ion? That's the next slide is. Okay. Okay. Ion formation. negative gaining or losing, but if you add electrons, it becomes negative anion. Losing electrons becomes positive cation. I've also heard pronunciation. Whatever. If some chemistry teacher wants to fight me on that, whatever. Anion and cation. Here's the really easy way to remember which one's which. Cation has a positive charge. And how do you spell cation? With a T. The positive is in the word. Okay? So all I want you to be able to do this week is, if I change the protons, you tell me what element it is. If I change the neutrons, you tell me how fat or how skinny, what the atomic mass is, or the number of neutrons. And the last thing is, if I give you ions, you tell me the number of electrons. And you guys are pretty sharp, so I imagine you guys are gonna do okay with this. All right? You are gonna need your periodic table every day, unless you want to memorize the periodic table.
Did that once.
Not interested. Even I don't memorize it. Why waste the brain space if you got the tool?
We had to for Miss Moore's class, and I actually used it.
I've studied chemistry for years and I still don't have the periodic table memorized. I don't expect you to either.
I remember.
We good?
No, not yet.
Okay. I'm not gonna change. I'm grabbing my coffee. Kingston's dead.
See, our poison finally worked.
All right. We're gonna do some last. We're gonna do some last examples with ions, and then I'm gonna let you guys off to do your homework, or at least start it. Okay. There are 2 homework assignments. One's with ions, one's with isotopes, because I want you to have good practice with both. The lab, all right, deals with a simulation like we did with balancing chemical reactions. Because I can't give you radioactive stuff and I don't want you to die on me, we're going to have to do some simulations for a little while. Okay? But if things go well, and assumedly they will, Aubrey, as I promised you at the beginning of the year, we'll probably bring out some blue black. Okay? I just don't like bringing it out because it just creates such a big mess. I have to clean up, and then I'm covered in cornstarch for days. Days.
Why did I get that one?
Well, it's like it's covered in the room. You'll understand what I mean once we do it. All right. Can we do some practice problems and we're good? All right. I think your brains are pretty mush already now. So.
My brain is hurting. We should hold it.
All right. Let's try this out. Okay. You're gonna need your periodic table in hand. All right. Periodic table in hand. Right, Meg? This is for helping that girl.
Oh. Thank you.
All right, for this first one right here, I give you an example. So fluorine has a negative charge. It has 9 protons, 10 electrons, and it gained 1 electron. In your homework, the table looks very similar to this. Okay? I give you some information, you fill in the rest. Okay? So for example, Hannah, you ready? First one. 53 protons. What element do I have?
Iodine.
Iodine, absolutely. So we got iodine. You just looked at that atomic number. All right. If it has 53 electrons, would you agree with me it'd be neutral?
Yeah.
But it has 54.
So
We've gained an electron. What's my charge?
negative?
-1. So how do you write that? You just write the atomic symbol with a negative charge up the top. That's it. Okay? Yes, Kinsey?
If we gained 1, why is it negative?
Because if they were equal, they'd be neutral. But in this one, we've gained an electron. If we had 53 protons, 53 electrons, it'd be neutral. But we have 54 electrons, which means we've gained 1 electron. We've gained a bad mood. We're now negative.
So how is it negative? It's just weak.
How is it negative?
Like the other one. The bottom one's +2, so.
Has +2. Do you want to hop straight to that one? We can.
She's trying to understand why there's negative
I'm fine with it. You want some? Alternate view.
Okay.
You want some?
Sure.
Kenzie, back to you. Ions are atoms that have gained or lost their electrons. If they've gained electrons, they've gained a bad mood, they become negative. If they lose electrons, they lose a bad mood, they become positive. Follow me there?
Yeah.
Okay, so you want to do this bottom one?
Yeah.
What's Ca?
Calcium.
Calcium. And how many protons does calcium always have?
Right?
Should be 20, right? I'm looking at the periodic table in the back.
So
So the number at the top is 20?
18.
Absolutely. It has 18 electrons because it is positive 2, means it has lost that negative mood. It's lost that, which means we've lost 2.
So it's the opposite of.
It's the opposite of what you think, which is why I use that analogy of a bad mood.
Okay.
Because electrons have a negative charge. But good connection. Yeah, Amy?
I'm confused how you got 18 for the electron.
18. So calcium, you got your periodic table in front of you? Always has 20 protons. If it was neutral, it would have 20 electrons. Good there? Positive and negatives would balance out. Cool? However, positive 2, it's happy. It's really happy right now. How do you get in a positive mood? You lose a bad mood. You lose electrons. So,
Oh, wait, I see.
follow me there?
Yeah.
Okay. So if we think about as electrons as a bad mood, people have a whole lot easier time of figuring out how many electrons there are. If we try to do the math on it, people get lost with the negatives and the positives. And once you get there, you got there, you're good. But good. Good questions.
Thank you.
Abby. Ready? Let's do the second one. I got 16 protons. What element do I have? Sulfur. Sulfur. And what's the symbol for sulfur? S, right? Okay. Now I've gained 2 electrons. So if I start with 16, I've gained 2. How many electrons do I have? 18, absolutely. I'm assuming you're right. I mean, I can barely hear you, okay? So we got 18 electrons. So what's the charge on it going to be? Negative 2, absolutely. Negative 2. Now, if you were to go to the Googles, all right, I've seen this written as 2 minus, negative 2, both interchangeably. I'm just writing negative 2 up there. You have, there, if we're being 100% honest, you're supposed to write it like this, but I think that is really confusing, and I don't understand why. So, me and a couple other people, when we teach chemistry around the world, we just put a negative 2 there. I've never, ever, ever, ever encountered a chemistry teacher who's that picky about it. All right.
Calcium's K.
K, last one.
Alright, it's got 19,
19,
and then since it loses 1, it'd be 18.
absolutely. Symbol is K.
Yeah.
What's the charge going to be?
What do you mean?
The charge. So we got negative, positive 2, plus 2. What's that charge going to be?
Plus 1.
Plus 1, absolutely. So you can put a plus or plus 1. Either one's okay. Fantastic. We good here? All right. I know it looked like a lot of information, but I guarantee by the end of the week, you guys are going to be perfect with it. You ready? Ready, Aubrey?
Yeah.
Okay. All right. We do have one last thing to do. All right. But we'll do that as far as our warm-up comes tomorrow. All right. And then you're off to do your thing. And you're off to your own volitions. You can do the ions and isotopes homework now. Okay. There are 2 different homework assignments, so it's worth 20 points. There's some solidness to it. Okay. And then Dawson, about your test, is that what you're asking?
Yeah.
Take your test when you got time. You can take it in class tomorrow, or you guys study all before school, after school. I don't care. All right. But if we need be, we can take it in class tomorrow. All right. Cool. All right. You guys are awesome. Keep it up.
You get paper towel water?
I sure did.